Good morning, everyone. Thank you all so much for coming to today's webinar. My name is Nicole Ostrowski. I'm with Rumsey. I'm the Marketing and Events Coordinator. And today I have Kurt. He's from Fluke. He will be going over motor and drive troubleshooting. So, Kurt, whenever you are ready, you can go ahead and get started.
Hey, good morning. Thanks, Nicole. And good morning, everybody. It's Kurt Keating with Fluke Corporation. We are what's considered sales engineers out here in the field. Appreciate you folks giving us the moment of your day here to get a little bit more involved with how to properly troubleshoot and maintain not only your motors, but your variable frequency drives as well. So a little bit on me. Been at this for a while here. So we'll the whole slide deck that we're going to be presenting today, by the way, will be available from Nicole at Rumsey. We're going to find a way to either post it or email it out to those who are interested. So feel free to obviously ask questions as we go. But what we're looking for is for some time to explain what we're going to do here today. And then you can ask questions in the chat box. I will address those at the end. But anything you feel like you might have missed, you're going to have an opportunity to get this entire training deck sent out to you. We also have a motor drive brochure that we actually developed with Alan Bradley a number of years ago. And it's actually being used in their training facilities on motor drive troubleshooting. So we have the ability of being recognized by them as an Encompass partner. And we're officially being used by their field service folks as well for this very application. So if we think about motors and drives and all the issues that are involved with those, I'm assuming all of you are on the line for one reason. Everything is not working absolutely perfectly as advertised. And there's a variety of reasons why. So we're not pointing fingers at any one thing in the motor drivetrain, but we want to address the entire drivetrain and really think about it as an entity connected and how things can translate from one part of that motor drivetrain to another and cause things to happen. So if you look at the slide that we're on right now, we have this training overview piece, and this is really kind of an idea of looking at the entire drivetrain from the input of the drive to the DC link to the output of the drive, what's called the PWM signal, looking all the way down that cable and going right into the electrical connection inside of my motor, making measurements there, and then considering the mechanical load that's out there as well, because all this is going to have an impact if you think about it. So there's lots and lots of issues and interests and ideas here in terms of where do I start. But we always think about, let's go look at the input side first. Let's go to the Gazinta, right? So we're going to spend some time looking at that. We're going to look at some of the issues around taking AC and turning it into DC, what's called the DC link, and issues that are around there. And then we're going to spend a fair amount of time looking at the output of that drive going out to the motor, what's called the PWM signal, and what are all the issues that are involved around that. And then out at the motor itself, obviously, we've got not only electrical issues, but we've got mechanical issues, right? We've got both going on there. So obviously, we appreciate your time. And it was very nice of you to spend this hour with us here today. Hopefully, we can enlighten you in a variety of ways. One of the couple of questions we're obviously asking customers is, why is this important to your work? Well, it's kind of a self-evident answer. Motors are doing majority of the really hard work inside of most buildings and facilities and plants. If I lose my motor or I lose my drive, what happens to the production line? What happens to my HVAC system? What is the impact economically and otherwise to me when those things go down? So a lot of customers have a variety of ways they address motors and how we manage motor problems. But the biggest single thing you want to think about is motors are an integral part to everybody's job traditionally. And motors are accounting for 50 to 75% of the electrical energy consumed in a building. Lighting is 15 to 20%, maybe 25. But motors are the ones that are really using the energy these days. So if we're running inefficiently, we're also wasting energy at the same time. So we're going to talk about different types of tools, different types of measurements, how to apply those, and then hopefully reduce downtime. because the downtime is the big issue. So most of you are on this line because things are not working properly. We're having downtime issues. We don't know where to start. And so hopefully we give you some guidance and some insight today in terms of how to go about this the right way. So the first part of this is the inverter technology. So if you think about it, when I had my motor, pump, compressor, fan, or blower connected across the line, I didn't seem to have a whole lot of issues. But the minute we put that drive in there, all of a sudden things start happening. So what we're doing here is real simple. This is a power supply. We're going to take three-phase AC or single-phase AC. We're going to turn it into DC, just like a power supply. But then we're going to do the inverse. We're going to take that DC and run it through a series of IGBTs, electronic gates, if you will. That are going to switch that DC on and off, pulse it, if you will, and create a signal that allows me to both voltage and frequency control that motor to allow it to do a variety of work. Constant horsepower, constant torque, variable torque, all so they can control that load to make it do the kind of work I want it to do. So that's the reason why drives exist today. So the first part of this is real simple. I'm going to take AC and turn it into DC, right? Again, a basic power supply. So what we're looking for is what is happening in that conversion process. Is that DC level where I need it to be? And then when I'm taking the DC output, am I actually creating the actual waveform output with the proper frequency control, with the proper voltage control to go out to the motor? And then the last part of this is we want to go look at the motor itself and what is the motor seeing. So again, what's coming out of the drive heading down 100-foot of cable isn't necessarily what the motor's seeing. There's going to be a change to that signal. I want to make sure that we verify what the motor's actually seeing, and are we providing it the proper stimulus to be able to get it to do the kind of work I want it to do. So the first part of this at Fluke, we're very big on the safety piece, right? I have a phrase I use all the time, and the marketing folks hate me for this. And, dead customers don't buy more meters, right? Well, there's slight truth in that, right? Not to poke fun at anybody's experiences, but we've all gotten shocked at different times. Some of us by our paychecks, but some of them actually off the circuit. We make sure the customers are doing all the right things, right? So, real basic, you're going to put on PPE gear. That's all there is to it. If we're going to go into a drive system and open up that cabinet, most of the time that's going to be a Cat 3 600-volt rated circuit. Drive could be 240, 440, 460, 480, whatever it might be, but if you understand, a fair amount of current's flowing through that cabinet. And so obviously we want to make sure that the meters and the devices are all properly rated. And I've got my PPE gear on myself, so I'm not going to get hurt in the event that I do touch a live circuit. So that's all the stuff you should be putting on, and you probably know this already, so I'm not telling you anything new. And no, we don't sell these things. Lumpy does, and so they can help you out if you're lacking for any of these types of PPE gear. But I obviously highly recommend all this has got to be on you per NFPA 70E. So first part of this, we want to look at the input going to the drive. We want to see what the drive sees. Now, I know a lot of you folks, and rightly so, are using voltmeters and clamp-ons, and we sell a lot of these, and thank you for that business. 72 years of selling this stuff. We know that's the most common tool that's going to be used out there in the market. But when I'm doing single-phase measurements, that's one thing, but when we get into three-phase measurements, there's a whole lot more involved with starting to look at the input to that drive. And so one of the things we want to make sure of is, do we have proper supply voltage? Is it balanced? What's the current draw look like? Is that balanced? What's the frequency going into the drive? And so I'm going to start to show you some wiring diagrams off of portable devices, things like motor drive analyzers, power analyzers, scopes, and the ability to be able to look across all three phases at the same time is pretty key here. The idea that I want to see relationships across the three phases is very detrimental if it's not properly set up to the drive, i.e. unbalanced situations are not going to be much of a friend to any motor drive at all. And we need to go see that first. So before we start blaming anything else in the circuit and start swapping things out, let's try right at the service entrance and let's go look at what we see. So here's an example of where we're going to start to look at not only the RMS value like you'd have in a multimeter clamp on, but we're also going to start to want to see what that waveform wave shape looks like, i.e. how clean is that power going into that drive? That is a key element here. It's got to be a nice clean waveform. So for those who are not familiar with looking at scopes, the red trace here is my voltage waveform, and the current trace is what my drive is actually drawing. And most drives and most computer-based control systems these days have what's called a switch mode power supply in them. So it's a capacitive diode circuit, and it's basically gulping current. So that current waveform doesn't look nice and clean sinusoidal anymore like the voltage does. But what we're really interested in is how clean is that voltage waveform? Is it harmonically distorted? Is it flat-topped? Is it balanced? And when we talk about balance, we're looking at trying the ability to look across all three phases at the same time. We'll show you some screens here in a second of what that's going to look like. But why are we looking there? Real simple. If my voltage is not balanced and not clean going into my drive, a lot of drives can't compensate for this and will end up not being able to supply the same out to the motor. The motor will pull more current, the drive will trip, and we will all blame the drive. That was not the drive's fault. It had everything to do with power quality, how clean and how balanced that is. So we'll show you this in a minute in terms of what that's going to look like. But while we're also out looking at this, we want to look at heat. So heat inside of an electrical cabinet, heat inside of a drive, heat off of a motor, or anything is going to indicate a overloaded situation, loose, dirty, corroded connections, and a real indicator there's a problem. So a thermal imager will show us heat. It won't tell me why it's hot, but it will show me overheated connections at switchgear, in switch disconnects in motor drive cabinets, and give me an indication that things are not right with the world. I've got a problem. So the idea is if we were using initially voltage current measurements and temperature measurements as an initial starting point, we can start to pick up when things are operating outside of normal operating conditions. So looking at connections, looking at fuses, looking at a variety of things that are connecting up to the drive will help me understand what's going on the input of the drive and hence what's going on the output of the drive. So use thermal imaging as a screening tool, investigative tool, looking at things under load. There is no value to looking at anything that's disconnected or off with a thermal imager. You're not going to see anything. And why do we want to look at it under load? Because we want to look at under its normal conditions and seeing is there a heat factor here as well. So all this rolls up to one thing. Can we use different tools to figure out what the root cause and the problem is on a drive system? And the answer to that is obviously yes. We can do not only voltage and current and power measurements, we can use temperature and a variety of other tools as we look down the drivetrain to help point to what we call root cause. So obviously there's probably quite a few on the phone right now who've had experience with either non-contact thermometers or thermal imagers. But again, a first pass tool is not a bad idea. Before I go connecting into a live circuit, before I stand right in front of that, what if I do a quick shot across that circuit with a thermal imager and determine do we have an overheating situation going on here? So we started talking about voltage and current unbalance. We're going to go back to that here. So hopefully everybody sees this, but the big one on a drive system, 2 to 3% voltage unbalance has real issues with a drive. A lot of drives cannot compensate if the voltage is more unbalanced than that. So what are we talking about? If I was using my Fluke voltmeter, I'd be measuring from A to B, B to C, C to A. Totalize it, divided by 3, find the average, and divide that divide the max deviation by the average. And we'll show you some calculations here in a minute. So if you actually wanted to do this with your voltmeter or clamp on, you can do that. What we're going to do is obviously want to preferably hook up across all three phases at the same time. So here's a diagram out of what's called a motor drive analyzer. Actually, one of the things we're doing for customers these days is we want to give you an actual presentation on the screen of the instrument. This is not out of the manual. This is right off the screen. How do I wire this up? Everything's color-coded, so it's pretty easy to follow in terms of connecting it up. And then go physically look at all those at the same time. Why do I want to do this? Again, if we have high current tripping going on. The motor is drawing excessive amount of current. Atypically, a lot of times it has to do with voltage being low and or unbalanced, and that's going to cause the motor to overheat by drawing excessive amount of current. And this nuisance tripping, as we call it, is going to be expensive. A lot of folks will again blame the drive. This is why this happened. The drive tripped. Must be a faulty drive. In reality, the drive didn't do anything wrong. That low voltage or unbalanced situation caused that constant tripping, which is costing you downtime and obviously loss of production time, which equates to lost revenue. All right. So harmonics are a similar scenario. What we want to look at when we look at harmonics, we want to look at how clean that voltage waveform is coming into the drive. And the idea of all this is am I having a nice clean sinusoidal waveform coming in from my supplier, my local utility, if you will, or is it harmonically distorted to the point where it's called flat-topped? So harmonics, for those who are not familiar with it, is multiples of the fundamental frequency. In the United States, 60 hertz is fundamental. That's my first harmonic. My second harmonic is 120 hertz. My third is 180, and so forth and so on. What's called THD, or total harmonic distortion, is nothing more than from my fundamental out to my 50th harmonic mathematically added together and presented to you as one number. What's called THD, or total harmonic distortion. Looking for is the ability to go measure not only voltage harmonics, but current harmonics. So if we do it in the single phase mode, as we're showing here, one voltage, one current input, we would be looking at them in a different way. So rather than looking at a waveform as an amplitude versus time, like we were seeing before, this is amplitude versus frequency. And the idea here is I'm looking to see how low this total harmonic distortion number is, and we were looking for something very low, 6% or less, right? And if so, where are those harmonics coming from? So we're looking at the spectrum across the frequency range, which again, the fundamental being my 60 hertz, or in this case, a 50 hertz. This was done in Europe. And then the other bars representing multiples of that. Traditionally, 5th, 7th, and 9th are typical harmonic levels that show up off of three-phase systems. And third harmonic is typical of single phase. So harmonics create heating. Harmonics will show up as an overheated circuit with a thermal imager. And harmonics are going to cause, obviously, with enough distortion, what's called flat topping of the voltage going into the drive system. Since it's a capacitive diode circuit on the power supply, and capacitors charge at the peak of the circuit, if we flat top the voltage going into the drive, then the capacitors don't fully charge, and the voltage amplitude of the drive doesn't reach its full potential, and hence there'll be a lower voltage going out to the motor. The motor will pull more current, the motor will overheat, and again the drive will trip, what we call the domino effect. Okay. So we're doing real basic things here, aren't we? This is troubleshooting 101. I'm looking to see what's going into the drive. I want to make sure that everything looks balanced, everything looks clean, it's not overheated, real simple. So a combination of something like a thermal imager and a power analyzer can help me figure that out pretty quickly. And again, we're looking at all three phases at the same time. So if we go to the output side, now we're in a situation where in the terminals inside the motor drive. And in the motor drive, traditionally, obviously, you're going to have three phases in, three phases out. But there's going to be a connection in the middle of this that says DC bus. And it'll be a plus and a minus screw terminal. And that's where the DC voltage level that the driver is producing can be actually accessed through use of a multimeter or a power analyzer. We're going to look at nominal output voltage and current. We're going to look for voltage and current balanced, in this case now going from the drive out to the motor. And we're going to start to look at this PWM signal. So what's DC bus? Well, real simple. It's an AC power supply. We took AC, turned it into DC. Okay. So we're going to go measure that, again, those terminals. We're going to be looking for not only the DC content, which we're hoping to see, but we're going to look at what's called the AC ripple or noise. And one of the reasons we want to look at it with something that's like an oscilloscope, we can see the waveforms, we can start to go measure those things. So if you take bus voltage, which is going to be 1.414 times the RMS line voltage. So we've got a 480 volt drive input You multiply that by 1.414, you're going to come up with a number that's going to be the 680 volt range, 680 volts DC on the drive. That's the level I'm expecting to see here. But what we don't want to see is we don't want to see an AC ripple or noise. And this is measuring now as a peak-to-peak value. The ability to use the scope is unique because we can measure not only a RMS value like a multimeter or clamp on, but we can start to measure also peak values as well, and peak-to-peak values to see the full extent of noise. So we're looking to see to make sure that we don't have any defective capacitors, and the diodes are possibly malfunctioning. And maybe it's a load application where this is being created. We're having a higher than normal AC ripple on there. And if you're seeing greater than 40 volts AC as a ripple, then there's a serious problem going on inside your drive itself. So again, why are we doing all this? Because we may have problems on the DC link where the amplitude of that is not fully outputting. I've got a flat top voltage. The capacitor is not fully charging. The output of the drive is dropping out to the motor. The motor's pulling more current and the drive's tripping. Again, not the drive's fault, but of course we're going to blame the drive, aren't we? Most folks would. So, what's the cost of doing nothing? It's just the cost of doing something. If we continually have these problems and it interrupts the operation of the drive and the motor keeps shutting down and the production line keeps stopping, add up every one of those occurrences, how much time was lost, how many hours it took to fix it, what kind of equipment did you need to replace. We add that up as an annualized number. That's called the cost of doing nothing. And that's going to continue. None of this is going to self-heal itself versus buying a piece of equipment to help me troubleshoot and get to root cause. In many instances, we could end up paying for ourselves in one outing. So that's the idea. You can't fix what you can't measure. So then we look at the output supply voltage, current, and frequency. Again, we're on the output side of the drive going to the motor at this point. And we're going to go hook up to those. And here's an example of what it'll look like single phase. We can do three phase as well. So you're going to have a series of pulses in the red and going positive, going negative. We're going to show you this in greater detail in a minute. And then the resultant current draw that's coming off of that. Drives control what's called the volts-hertz ratio. So the amplitude of the voltage and the frequency going out from the drive to the motor of 0 to 60 hertz is actually done electronically through these gates. And we're pulsing these at a certain width, what's called the carrier frequency, to create this pulsed DC that now looks like an AC waveform to the motor, what it's going to draw current against. So if we don't have proper output, again, things are not going to work properly. So we're going to go measure the output of the drive now. We're going to start looking at all three phases. We're going to look at across all three phases again from the drive to the motor, as we did on the input of the drive. If you were going to do this the old-fashioned way, the manual way, either using a voltmeter for looking at voltage unbalance or current clamp for looking at current unbalance, here's what this calculation is going to look like. So again, we were talking about 2 to 3% unbalance or greater than that being a problem on the input side of the drive. It's equally as much a problem on the output side of the drive going to the motor. So we want to have a nice clean waveform coming in. We want to have good amplitude. We want to have no AC ripple, and we want nice voltage going out to the motor, and it all has to be balanced. Balanced as in the amplitude of all these need to be fairly close to each other within 2 to 3%. So if you start to look at this stuff with a scope, this becomes really tough. And it's even harder with a multimeter or a clamp-on. And here's why. Because multimeters and clamp-ons were set up to measure the full frequency bandwidth of a circuit. If you use an example of our 87.5 multimeter, it reads up to 20 kilohertz. So not only are we going to read the fundamental voltage, we're also going to read the carrier frequency. You're going to end up having a reading on your display that's not going to agree with this drive at all. And the readings on both the frequency and the voltage are not going to be similar to what the drive is displaying. But the big issue is we want to look at all the three phases at the same time, and we want to see it graphically. So again, you're going to see a series of pulses, positive and negative. Each one of the phases is colored. A is red, B is blue, and C is black. But this just looks like a whole lot of squiggly lines on the display. But we are going to be able to measure these, and because it's an oscilloscope on a motor analyzer or a power analyzer, we can zoom in and get down to individual pulses. So again, what are we looking for? We're looking for balance, right? If I don't provide balanced voltage to the motor will pull more current. They're a constant power device. You give it no choice. I pull more current, the motor heats up, the drive trips. Again, domino effect. So this nuisance tripping problem, obviously we talk about quite a bit, but that's very common. We see a lot of this. It can also because of elevated motor temperatures, which again, why is a motor temperature going up? Well, could be a mechanical problem, could be electrical problem, but in either case, there is a problem causing the motor temperature to go up. And again, that's causing all sorts of problems on the drive system. So what's current unbalance? Again, I'd have to take three clamp meters and try to measure all these at the same time. We can go do that with a power analyzer or a scope meter. Again, I don't want to have high unbalance of current draw across these three phases. What's that telling me? Well, that's telling me that voltage is probably unbalanced, or there's an excessive amount of resistance on one of the connections or the windings that's drawing more current inside the motor. But in either case, that motor is going to get hot as a function of that. So we're going to start to look at things like current draw. Now you'll notice this is now what appears to be or looks like a regular sine wave, but it's slightly choppy if you look at it fairly closely. This is the resultant current draw off of that PWM signal that the motor is drawing current against, and now showing these three. Now, as you can see, we can see the waveforms, we can also see the currents, and we're running this unbalanced calculation live on the display for you. If you were doing it with a voltmeter and a clamp on, you'd be standing there constantly with the calculator, pencil, and paper and running these constantly. So imagine we could look at this over time. How balanced or unbalanced is the load? How balanced or unbalanced is the voltage and the current going into the drive? And we can use these as a babysitting tool for looking at it over a period of time. A lot of issues in electrical systems don't happen when you're there. Now, the rule of thumb is it's rock solid when I'm looking at it with my voltmeter and clamp on, and 2 hours later all heck breaks loose. So what if we could use this as a babysitting tool for looking at how balanced or unbalanced that circuit is on voltage and current over time? And we can. So again, we're looking for elevated currents, elevated motor temperatures, and obviously elevated temperatures can cause windings and insulation on windings to burn up. So the PWM signal that we're actually looking at, again, is a series of gates going positive negatively. Basically, it's pulsing this DC bus and generating this frequency. So the carrier frequency is this series of gate times that are on and off, but the overall waveform it's creating is 0 to 60 hertz. So that's how it's able to get the motor to speed up or slow down. And we are also controlling the amplitude, so we can do things like constant horsepower or constant torque or variable torque over time. So we need to sample this quickly, don't we? If we're going to go measure these little pulses, and they're high frequency pulses, I'm going to be starting to look at stuff that looks like this. So those pulses are not going to be anything like a regular waveform now, are they? Not what the drive is seeing on the input side, that's for sure. And I want to make sure that the readings are correct. So here's the little gotcha. Ready? Bottom of the page. VFD's displays are calculated values, not read directly. These are calculated in the electronics version of the drive. It's not reading it directly like a voltmeter or clamp-on would. A Fluke scope, a power analyzer, or motor drive analyzer has known accuracies, and Fluke can provide an NIST certificate of calibration on any of these products, so you can use them as a traceable reference. There's no such thing as a calibrated motor drive. That doesn't exist, nor can I get one certified. But I can certify my meter, I can certify my scope, my power analyzer, and use this as a reference. So if I'm claiming capability of being traceable back to the national standards on a portable device, and I've got a drive display, which one am I going to believe in or agree with? The portable meter, and we will be much more accurate than the drive ever will be. So the ability to cross-check what is the drive telling me, is it giving me the truth, and are the readings making sense? And maybe then, and only then, could I say, I might have a defective drive on my hands here, because what it's telling me it's outputting, what it's actually outputting, are two different things. So last part of this we're going to get into are what's called the output reflections, and a variety of other things are going to happen. If I've got a long cable run, and I'm going from the drive out to the motor, and let's say that's 100 feet plus, and in some instances we've seen upwards of 200 feet, you have X amount of resistance, capacitance, and inductance per foot on a wire. That capacitance can cause this coupling effect and create this overvoltage reflection. It's going to be high amplitude voltage that's going to hit the first couple of windings, turns on the windings on the motor, and it's going to cause it to degrade. So we would, in a lot of instances, call these spikes if you were going to look at it on a regular power line. But here we're going to call them output reflections. So normally I'm expecting each one of these PWM pulses to be universal in their amplitude and not have any what are called transients or spikes that are coming off of these things. And believe it or not, these could be several thousand volts. And so they're a function of, again, high switching speed on the output side of the drive and the IGBTs, and then we couple that with this long cable run, which is very capacitive, and causes this overvoltage reflection to occur. Now, I can't read this on a multimeter clamp-on, can we? No, you can't. Why? Because we're going to measure peak of the waveform. So peak measurements and or peak-to-peak measurements are unique to power analyzers and scopes, not something traditionally I can do with my voltmeter clamp-on. A voltmeter clamp-on is always going to measure the RMS. So we're going to take the peak value and multiply by 0.707, which is going to be the RMS value, not the peak value. So we have the ability of reading several thousand volts with a peak with a power analyzer or a voltmeter, a motor drive analyzer, whereas I can't do that with my voltmeter and my clamp-on. So what this is going to happen if I have these high voltage reflections on this long cable, it's going to may exceed the insulation rating on the motors. What are called inverted rated motors and inverted rated cable are highly recommended to use with a motor drive. And if we start to have these very high peaks, this can actually cause real damage inside of the motor itself and cause the windings to break down and or eventually short. So as I increase that voltage amplitude, I'm going to increase the heat factor. The insulation is rated for a certain temperature, and at some point it will break down and it can fault. And if you think about a motor, how many different ways can we fault? 6. A to B, B to C, C to A, A to ground, B to ground, C to ground. I get 6 fault paths on a motor. Only takes one, bam, done. So now I've blown the motor up as a function of having insulation failure because I have high voltage amplitudes that are causing an overheating effect, causing insulation to break down and causing it to fault. So what if we could go measure these? Now we need a high resolution scope to do this. So again, a scope meter, a motor drive analyzer is high speed. Traditionally, we're looking at 60 megahertz above. On the motor drive analyzer, we are up in the 500 megahertz range. So the ability to go measure those amplitudes and see each one, including individual pulses. So I can actually go read one. We're in the 200 nanoseconds per division here. Okay, I'll equate it to you, those folks who are using multimeters and clamp-ons. Your multimeter clamp-on updates 3 times a second. So every 333 milliseconds, I get a new reading. We're reading into the nanosecond and even the microsecond domain. This is way beyond the ability for a regular multimeter clamp-on to see, but not obviously for a high-resolution scope. So the peak voltage can be 2 times the bus. So if the bus voltage is 680 volts or 700 volts or higher, and they can be, you can have voltage amplitudes that are exceeding the 1400 volt range. a lot of insulation on what's called an inverted rated motor are now set up and designed to work up to 1600 volts AC. But it's only a 480 volt service, so why so high? Because these overvoltage reflections can actually get that high. And we want to be able to read those and know that this is actually happening. So the reason for this scope is I can go read the voltage amplitudes as a peak value or a peak-to-peak value and know how high that voltage amplitude is hitting the motor terminals. So we're going to read it two ways, on the output of the drive, and then we're going to read it again at the motor terminals. What is the motor seeing? Okay. So we're going to have a noisy motor. We're going to have motors that seem to prematurely fail. We're going to have cable that seems to prematurely fail because they're not properly rated for the inverter application. So they're not inverted rated motors and inverted rated cable. So we want to measure that peak-to-peak voltage. We want to measure temperature. And solutions are real simple. Shorten the cable, put a low-pass filter on there, rewind the motors so they've got the higher insulation value. In some instances, you're going to need to replace the bearings because the bearings are going to be electrically distorted as well. We'll get into that in a second. So, again, what are we trying to do here, folks? We're trying to keep things running longer, cooler, more efficiently, right? Less breakdowns are better. Obviously, loss of service on anything, whether it's an HVAC system or a motor driving a conveyor line, are going to have a negative impact into your business model. Avoiding the tripping situation that's constantly going on, and be very cognizant of how much life I've got left in the insulation and the windings of my motor, and determine how long can I go run that thing. So everything dies, right? I think we all agree on that. There is no such thing that lasts forever. The question becomes is, when is it going to die? So if we could use test equipment to determine the when prior to failure, we could not have you being surprised at 5 o'clock on a Friday afternoon. Right? So we're going to measure all these things. We're going to document all these things, and we're going to compare them against the known standards in the marketplace to determine are we operating inside the acceptable boundaries or outside the acceptable boundaries. So the last part of this is we're going to get into the motor and the drivetrain measurements. So once we've moved beyond the motor, then we're going to start to look at the load. So the load obviously is going to have an impact all the way back to the VFD, isn't it? So what we want to do is make sure to see what is the motor. And we're going to start back up with the idea of, is there an overheating effect or a thermal degradation that's going on as a function of the load at the motor? So we're looking there, right there is the actual motor and the coupling, and is there overheating? So is the overheating happening on the electrical side? Is it happening on the bearings? Is it happening on the connection itself? We can obviously go look at that load. We can go look at that pump or that compressor, that blower, that fan, and go see overheating as well. There's an example. So how much heat is there? Where is it coming from on the drivetrain? And what is going to be the problem? So how many folks know this one? So if we talk about overheating on a motor, and if typical motor rating is 40 or 50 C, for every 10 degree rise above nameplate, so if I'm operating a 40 degree C motor at 50 degrees, 10 degrees above, I'm going to lose half the life of the insulation of the motor as a function of heat. So again, how's that happening? The load and or a variety of things are causing that motor to draw an excess amount of current because of a low voltage or a variety of other reasons. It's unbalanced. The motor is pulling more current. The motor is heating up. It's going beyond that 10 degree rise. The insulation is becoming brittle and cracks and faults, and the motor dies as a function of heat. This can also happen if you don't have proper cooling, right? If I take this motor, put it in a room, lock the door, shut down the airflow, and run this thing constantly, you'll cook it in its own juices, so to speak. It'll die a premature life because of the fact that there was no airflow going across the top of those fins to cool it off. So those are heat sinks. If you look at those fins that are on the top of the motor, and I'm expecting airflow to go across it. So if we put dust and dirt and grease and grime and everything else on top of that to reduce the heat dissipation coming out of the inside of the motor to the outside of the motor, that'll actually have it die as well. So looking for the hot spots, trying to figure out why is it hot. Makes perfect sense. So why is a motor overloaded? Well, the other end of this is the load itself. So if there's too much torque, there's too much demand on the motor. Obviously, the motor can't handle it. It's not properly sized for it, for example, either electrically or mechanically, and you can have either one of those two factors come into play. Then the motor is going to be dying a premature death. Okay. So one of the things we came out with Fluke a couple of years ago, it's a really interesting tool. It's called a 438-2. This is a three-phase power analyzer, but it's also motor efficiency analyzer as well. And we can do mechanical efficiency as well as electrical efficiency in one. And we do everything off the electrical side of the circuit. We do not have to have a torque or speed sensor connected onto the drivetrain in order to do what we're about to do. We do everything off the electrical side. It's a really interesting tool. So if you turn this box on and we hooked it up onto your motor drive, and we're going to be on the output side or on the input, either one, we're going to plug in all the nameplate of the motor. What we're trying to do is we're going to take those characteristics of that specific motor, and we can compare it to a known database we already have in the box of all these different motor types. And we're going to be able to show you live off just the electrical side how efficient it is on kW, power factor, percent unbalance, and harmonics. And then on the mechanical piece as well, the actual mechanical horsepower, foot-pounds of torque, speed, and mechanical efficiency. And we can run all this live at the same time. The idea here is the motor properly rated for the application according to the NEMA readings? So we put a motor in the circuit, we put a load on it, that type of motor keeps dying. Is that a good electromechanical fit? Maybe it is, maybe it isn't. So what if we could actually take those readings and we can plot it up against what we call the NEMA derating curve live while it's running under the actual load conditions you're using it on. So this is not like you're taking it out to a motor test stand and they're trying to simulate what the actual load is. This is the actual load. And we're trying to determine, are you inside the acceptable range or are you severely oversized for the application? We're down here in the 50% or lower range. Or are we up in the red zone here where you're overdriving the motor? It was never designed for the type of load that you're putting on it, and that's the reason it's dying prematurely. So what are the detriments? On this end, obviously, motor's not going to last as long as we expect them to. On this end, I'm wasting energy. It's not a good fit. We see a lot of this with fans and motors driving HVAC systems. They oversize the fan, oversize the motor, and we create this excessive air turns through the building. And that's all well and good, but the reality of it is I'm blowing a lot of conditioned air out of the top of the building, and I'm wasting a ton of energy. So it's not right size for the application. We want this thing to track on this yellow line as we're running it. So as we're changing load, and you might be saying, okay, well, I've got a high speed and low speed on my fan system on my HVAC. Yeah, we want to look at it in both of those settings and see is it properly rated for that usage model that you're using it on. Neat idea, right? So we want to extend motor life. Motors are expensive. Not 25 horsepower motors, but 200 horsepower motors are, 300, 400, 500, right? Do I have a backup? If I keep losing these motors, what's that cost me? What's the downtime? What's the economic loss to me? What's it cost to replace a 200 horsepower motor versus repair the 200 horsepower motor? If I could fix it before it goes to full failure mode, and we can, you can breathe new life into that device, but we have to be able to figure out the when it's going to die before it does. So if you'll notice something, we're kind of talking about predictive maintenance here, aren't we? And if you think about what we're doing, it is all a form of predictive maintenance. But a side benefit, we're also going to find things are running inefficiently, not properly rated, and you're wasting energy. And again, 50 to 75% of your electric bill in an average building are motor loads. So bearing failures are kind of the last part of this. Hopefully you guys are still hanging with me here. There's a lot here, obviously. So what are bearing failures? So bearing failures don't start out as bearing failures. Bearing failures start out as a variety of things. And one of those things are what's called shaft voltages, which create bearing currents. So this is an electrical failure inside of the motor system that's actually causing bearing failures and misshaping not only the bearing race, but the bearings themselves. Okay. So we first use the thermal imager to see the overheating effect. So if I've got very high heat on either end of that motor, either the driven end or the non-driven end, why is it hot right at the bearing? That becomes the next question. All right. And what we're looking for, if you look at the bottom of the screen, properly maintained lubricated motor bearing should not typically be more than 5 degrees C warmer than the motor casing. So, rather than using a non-contact thermometer, if I use a thermal imager, I can compare those two, can I? I can see that temperature difference and clearly see where that heat factor is coming from and see the fact that it's 5 degrees C warmer. So, again, temperature differential of more than 10 degrees C, they indicate the bearing needs repair replacement. Okay. So why are bearings getting hot? So one of those things could be mechanical. What if we have misalignment? What if we have looseness? What if we have other issues mechanically that are going on and causing the bearings to fail? So very typical. Again, bearings aren't going to just fail. Bearings fail for a reason. Right? So the things we do at Fluke, obviously, is the idea of I'm going to look at thermally as a screening tool, but we also want to look at what's going on inside the motor if I'm having excessive currents and the motor is getting hotter as a function of that. What's that doing to my insulation? What's going on with the bearings? We're going to start to look at the insides of this motor now in terms of looking at this. So the first part of this is let's talk about the heat factor. So as motor windings deteriorate, again, the potential for short circuit can occur. So I'm assuming a lot of you have probably heard these tools. I don't know if everybody using them or not. What's called a megger, and that's a general term. We call it an insulation resistance tester, or an IRT. The ability to be able to test across my motor. Now, this is a power off test. You're never going to measure a live motor. We're going to measure the drive either, for that matter. That gets totally disconnected. But what we don't want to look at is we want to look at the resistance value in low ohms from each phase to the next, A to B, B to C, C to A. Typically, you're going to see 1 to 100 ohms, something in a range. We want to see balanced resistance, right? 5 ohms, 5 ohms, and 5 ohms. We don't want to see 5 ohms and 5 ohms and, let's say, 10 ohms, because that one leg of the motor will draw twice as much current, won't it? And then the motor's going to get hot. But our big concern is how much resistance is there, what's the health of the resistance from each electrical phase to ground. So in a motor, the green ground screw inside the electrical connection is ground. The case of the motor could be ground, but only if you've scraped off the paint, and then we can get to it. The shaft of the motor is not ground. So we're going to test from each phase to ground, and we're looking for a very high resistance, ideally. And we want to see greater than 1 megohm or 1 million ohms per kilovolt. So the rule of thumb is twice the operating voltage. So if I got a 480 volt motor, I'm going to test it at 1,000 volts. If I got a 240 volt motor, I'm going to test it at 500 volts. And if I got a 120 volt motor, I'm going to test it at 250 volts DC. This is non-destructive, but it will electrically stress it. And we're looking for what's called leakage current, similar to testing your plumbing abilities at home. Mine are not very good. Anything I touch in plumbing seems to leak. But if I increase the pressure on my water line and look for leaks, that's equivalent to what we're doing. We're increasing the voltage pressure into the motor between each phase to ground by doubling the voltage and looking for leakage current to see how much resistance is left in those motor windings. So obviously, this is a way of determining how much electrical health. And if you think about an insulation tester, this is go, no go, isn't it? Right? If I got a low reading here, now's my idea to take it out of circuit now before it dies. And it will die. Now you're on the negative slope of the lifespan of that motor. And we want to catch that, don't we, before it dies? Because if it does die and you blow it up, you might not have any life left into it to repair it. We want to be able to repair it still, right? As opposed to destroying it and having to replace it with a brand new one. So Catastrophic failure is kind of what we're looking for. And again, if it fails, you're going to have downtime. Right. Shaft voltage, kind of the last couple things we'll hit on here. So high frequency PWM voltages. So again, this carrier frequency that we're talking about. So this is the width of the pulses that the drive creates to create the frequency to drive the motor, are set anywhere between 4 and 14 kilohertz in the frequency range. The higher the frequency of those, the higher the voltages can be capacitily coupled to the stator and to the shaft of the motor. And if we have excessive amount of voltage flowing from the case of the motor to the shaft of the motor, typically 8 volts or higher, AC that is, then you can have voltages starting to create current flows through the race of the bearings and the bearings themselves and actually start to cause them to misshape. So one of the things that's been on the market for a long time, and we've now incorporated into our motor drive analyzer, is what's called an Aegis wire brush probe, AEGIS. And that is a wire brush probe that literally connects, as you can see on the illustration, from the case of the motor on an unpainted surface, so that's your ground, to the shaft, and we're going to measure both the voltage and the frequency of that voltage. And again, if it's above a certain voltage amplitude, we know that currents are going to start to flow in the race and the bearings of the motor. And so you'll have what's called these flashover events. Now, look at the time domain here, folks. 40 nanoseconds per division. Am I going to see that with my voltmeter or clamp meter? No, no way. Too slow, way too slow. I'll never know this is happening. So we use a high frequency scope to be able to capture these events and look at the number of these discharge events by amplitude and by width, less than 50 nanoseconds. So these are real short pulses that are basically arcing across the bearing and the race of the bearings of the motor. And the higher the voltage amplitude, the more severe this is going to be. So notice the amplitude shifts 7.5 to 11.3, 11.3 to 15, and greater than 15 volts. That's almost double the voltage that we really want to see there. And this is really going to cause this motor to deteriorate quickly. And you're going to basically kill it electrically. This is what this looks like. For folks who've ever had a post-mortem done on your motor at a motor shop, they can actually show you this fluting. That's why the motor died right there. This was an electrical breakdown caused by high frequency coming out of the drive, going to the shaft of the motor, causing currents to flow in the motor. That's why it died. So if we can go measure it, we can go fix it, can't we? Now, how do I fix this stuff? I'm going to go back a couple two screens here. So folks have probably heard what's called an Aegis ring, AEGIS, same as the wire brush probe. It would fit here. And it would actually allow us to be able to shunt away those voltages so that we don't have currents flowing. But they're expensive. I don't necessarily want to put them on every motor unless I have to. So what if we can actually see the occurrences happening with a motor drive analyzer and know that we need one of those? We go put the solution in place, the Aegis ring, and then we go measure it again and know we've fixed the problem. Problem went away, right? And it's a basic troubleshooting philosophy. I measure, I put a solution in, we measure it again, we know we fixed the problem, we're done with that, move on to the next thing, as opposed to guessing. So the whole idea of test equipment is not only to initially find a problem, but to confirm the fact that you fixed it and it went away. So it fills two buckets. Last but not least is the mechanical piece in the remaining minutes that we have. Obviously, all sorts of misalignment problems. More than 50% of bearing problems start out as misalignment. That's pretty typical. So you can have any number of parallel or angular misalignments happening here. And as a function of that, we're going to cause vibration to occur. That vibration is going to start to translate into the bearings and the race of the bearings of the motor and eventually cause the bearings to fail. So we make a model called an 810 and an 805, a little handheld unit. Either one can point up the fact that we have excessive amount of vibrations, both overall vibration, which would be misalignment, unbalance, and looseness, and then bearing vibrations, which is going to be very high frequency that we can see and tell you where it is. So this particular device has 30,000 different motor drive types already built into the firmware. So we have a known good database we're going to test your device against and show you where the severity of the problem is. This is a 1 to 100 severity scale. That's years, months, weeks, days. If you can hear it, if you're the guy with the wooden dowel, the screwdriver, the stethoscope, it's too late. You're within probably the last 4 weeks of his life or less, if you can hear it. And we're talking about frequencies that are way beyond human hearing that we can pick up with a triaxial accelerometer that hangs on the end of our tester and give you months worth of advanced warning that these vibration problems are occurring. And want to capture all that prior to failure and pull or replace before we hit breakdown. So that's why a vibration tester fits in well for the application. And there's what it looks like. All right, unbalance, same thing, right? So if I don't have things properly balanced, and we can cause, it's an idea, fan blades on a fan that get covered with dust and cause it to create a wobble. That's an imbalance as an example, what that would be. So we can go measure imbalance and see that things are properly balanced. If they're not, we're going to tell you they need to be. So we're looking for indications of motor mechanical wear using a vibration tester. We're going to use a thermal imager to see the heat factor. And again, if we're going to look for bearing breakdown, we can also do a shaft voltage measurement. Looseness is, again, exactly like it sounds, excessive clearance. Okay. Can also start to cause bearing problems to happen. Measure that as well. So, premature motor wear or damage, overheating, motor failure, and again, all relates back to one thing we're all trying to avoid. That's the downtime and the economic losses that occur every time I have my production line down or my HVAC system dies. Obviously, this is all going to negatively impact your bottom line at your business. So, motor drive, real simple. Obviously, I'll be using mechanical tools to determine, am I mechanically aligned? Do I have unbalanced looseness situations? Are there bearing noises that I'm starting to pick up as a future indicator of a future failure? And we can see bearing problems with this type of device anywhere from 6 to 9 months out and start to know that we have a bearing failure imminent and predict that future failure and plan for a proper shutdown to repair and replace. So in summary, and the last remaining minutes that we have, I'm using a variety of tools to determine problems. Again, we use the phrase root cause. You can't fix what you can't measure. Otherwise, we're going to guess. And what we get into guessing games, and I see a lot of this, we get into swapping. We're swapping the drive, we're swapping the cable, we're swapping the motor, we're trying any combination of things we can do, but we're never have the ability to actually identify root cause and fix root cause. So that problem becomes persistent and is really never going to go away. This does require graphical measurement capability. It does require something that allows me to look at waveforms now. My voltmeter, my clamp on only take me so far, but they have no ability to store data. I can't measure a peak. I can't document anything off of these. I can't leave them on the circuit for an extended period of time to see variations or intermittent problems. Whereas we can do all that with these types of devices. So here's the typical lineup. And we have talked about all of these. The last part of this is, obviously we would love to have another conversation with you on another day, if we can. The idea here is we didn't want to make this end-all, do-all. We would like to have this as the beginning of a conversation with you, the customer. What are you seeing? What kind of issues are you having? Can we at Fluke help you with that and help you create a program where you can save time and money in production, lost time, simply by having the ability to be able to measure proactively to look for future problems. So here's our offer today. There's a QR code sitting on the screen right now, but we're going to send this to you as well. All right, if you can scan that with your mobile device, I'll leave it on there for a while, and you can scan it. Here's what's going to come out of this. We're going to allow you to fill out a form, and we're going to send you a completion certificate on your motor drive troubleshooting webinar today. We're also offering you an additional discount, only good through Rumsey, via Fluke, towards the purchase of any of these types of devices today. It's going to be good for 60 days. And again, it's only good with Rumsey. If you have questions, we're more than happy to answer them. And if you want to take a picture of that along with a QR code, there's my email address and my phone number. I'm based out of Bethlehem, Pennsylvania, Lehigh Valley area. I cover the Philly metro area and Jersey. For those folks who are in that part of the line, we have two other sales engineers. Doug Dunn, who's on the line today, is our guy covers south of the Mason-Dixon line, the southern tip of New Jersey, Delaware, Maryland area. And Derek Kosmarek, my other counterpart, covers up in my neck of the woods, up in Lehigh Valley, and then north, all the way up to the New York border and into New York State as well, I might add. So we're very much interested in having a future conversation. Look forward to you taking advantage of the additional discount through Rumsey. All right. Appreciate everybody's time and the interest. Thank you so much. And you all stay safe. Let us know how we can help you at Fluke.